My name is Harnit Saini. I am assistant professor in Akgec Engineering College, and today is the topic we are discussing is groups. It is the topic of DSTL in second year. Now let's start with it. First of all, when we want to know about the groups, we should know about the binary operations. A binary operation on a set is a rule for combining two elements of the set. More precisely, if S is a non-empty set, a binary operation on S is mapping F, S into S gives S. Thus, F associates with each ordered pair xy of element S and element fx of xy of S, right? When we are performing any operation, right, like example, the operation of addition and multiplication are binary operations on set of integers. Since for every a and b belonging to integers, a plus b also belongs to the integers, and a into b, the product of both, also belongs to integers, right? They want to say if a is an integer, b is also integer, then a plus b will also be an integer and a cross b will also be an integer, right? The operations union and intersection are binary operations on the power set of a non-empty set S. Since A union B belongs to the power set and A intersection B also belongs to the power set, A and B are the subsets of S, right? Like in the binary operations where addition and multiplications are same, if the operands are same, then the product and sum will also be belongs to the same class of integers. Similarly is the case with the sets also. If intersection and union belongs to the power set, then if A and B belongs to the power set, is a subset of S, then their union and their intersection will also belong to the power set. Now other binary operations, if from any A we get an A, then it is a unary operation. When we are performing the operation on a single operand, then it is called a unary operation, and if we have involved two operands, then it is called a binary operation. If three, then ternary, sim, and so on, right? Now properties of binary operations. If star is a binary operation on set A, then closure property. According to this property, if an elements A and B belongs to A, then the relation, their relation also belongs to A. As was the case with the integers, if A is an integer, B is also an integer, then A related B, this relation may be plus, may be multiplication, will also belongs to an integer. So if we are able to prove this property, then we can say that it satisfies the closure property. Then is the associative property. Associative property says if the elements A, B and C are belonging to A, then A star B star C is equal to A star B star C, right? If we are performing an operation on this and answer of this with operated with C, we will get the same answer if B and C are operated first and then we operate C on that. If it satisfies this, then we are able to say that it is satisfying the associative property. Identity element. There exists a unique element E in set A such that for any element A belonging to A operated with E, we get A again, right? If we operate A, E, we get A. If we operate E with A, then also we get A, right? Such type of element is called the identity element, and it also belongs to the same class to which A belongs, right. Then E is called the identity element of operation star. This star can be any operation. It is not that you would have to take only multiplication or addition only. It can be any binary operation, right. Inverse means if for an every element in set A, there exists a unique element A dash in set A such that if we are operating an element with an inverse, we get the identity element. If we are able to get this and inverse into A, will get identity element, right. And if we are able to operate this, then this element is called the inverse of that element in that set, right. Commutative property, if A star B gives some answer and B star else A also gives the same answer, then it is called a commutative property. Cancellation property, if the elements A, B, C belonging to A, then A star B, A star C, we can cancel A from both sides and B is equal to C. If we are able to get this, then we can say that cancellation property is satisfied here. Distributive property. Now in distributive property we require two operations. This is not product or sum, it is implying that we are having two operations. One is implied by star and other is implied by the plus symbol, right. If one symbol is outside, then this outer element will be distributed with the both the elements and we will get the same answer in this, right. And if we are getting this, then it is satisfying the distributive property. Now the algebraic structure. A non-empty set G along with one or more binary operations is called an algebraic structure. When we are operating some of the operations on some of elements, then it is called an algebraic structure. Example, if G is a non-empty set, star and dot are the binary operations, then G star and G star dot, G dot are all algebraic structures. For example, n plus, I plus, natural numbers, integers, negative integers, real numbers. If they are operated on plus and product, then they are all algebraic structures. Now what is a semigroup? Now based on these properties, we will divide the various categories of the sets in which we can keep these elements, right. An algebraic structure G, where G is a non-empty set and star is a binary operation, is said to be a semigroup if the operation star satisfies the following properties. First of all, the two properties should be satisfied, closure and the associative property. What does the closure property says? It means that this star is a binary operation and if A and B belongs to some set, then their operated element, whatever we get after the operation, this also belongs to this. And associative property says if A star B is operated first and the answer is operated with C, we will get some answer here, and if B and C are operated first and then we operate A on it, we will get the same answer, and this will also belongs to this set, right. If these two properties are satisfied, then we can say that the set which we are talking about or the algebraic structure we are talking about is the semigroup, right. Now monoid. In semigroup we were having closure and associative. Now we have added one more property, that is identity element. If in addition to closure and associative property we get the identity element also, then it is called a monoid. Let's read the definition. An algebraic structure G, where G is a non-empty set and star is a binary operation, is said to be a monoid if operation star satisfies the following properties. First is the closure property. It means that the operation star is a binary operation. A star B belongs to G. If A and B belongs to G, then A star B will also belongs to G. Associative property, again we have discussed already. First we will operate the first two elements and then we will operate the third on it. And secondly, if we operate the last two elements and operate the first one on it, both will give the same answers and they will belong to G only. Identity element. There exists a unique element E in the set A such that for any element A star belonging to set A star E will give A and E star A will also give A. This E will also belongs to A, right? If we are satisfying these three properties in a particular algebraic structure, then it is a monoid. Now group. What is a group? An algebraic structure G where G is a non-empty set and star is a binary operation is said to be a group if the operation star satisfies the following properties. Okay, we have done closure, we have done associative, we have done identity. Now the fourth property is added to it, that is inverse. Now if we are able to satisfy closure, associative, identity and inverse properties in a particular algebraic structure, then it is a group. Now what is closure property? We have already discussed that if A and B belongs to G, then their operated element will also belong to G. Associative, again first two elements operated and then C, second two element operated, then applying A, both will give the same answer and it will belong to G. Identity element says that it is that element if operated with the group element, it will give the element itself, right? And that element will be the identity element and it will belong to A. Inverse, if there exists some element which when operated with the other element gives the identity element, right? And this element is also belonging to set A. If they are any algebraic structure is satisfying all the four properties, then it is a group. What is a abelian group? Now the four properties of the group are there. When we add fifth property, that is the commutative property, right? Closure property we know, associative property we know, identity we have already discussed, inverse we have discussed just now, and commutative means if the elements are operated like this, if the first element is A and in right hand side it is the second element and but they are giving the same answers, then it means they are commutative. And if the algebraic structure is satisfying the five properties, then it is a abelian group. Now finite group or infinite group. Finite group means the elements which are there in that algebraic structure, we are able to count it, means finite number of elements are there. And if it is a infinite number of elements are there, then it is called a infinite group. Let's check the example. Suppose G1 is a group and it is having these four elements, we are able to count it, then it is called a finite group. But G2 is some element on like addition and it is having integers or natural numbers on multiplication and it is vast number of elements are added in this group. So we are not able to count it, so it is an infinite group, right? Order of the group means the number of elements in the group. The number of elements in a finite set of group G is called the order of the group and it is denoted by OG, right? OG. Like G1 is equal to 1 minus 1 iota and minus iota is a finite group and the order of this group is 4 because it is having 4 elements, 1, 2, 3 and 4. Properties of the group. Uniqueness of an identity. The identity element in the group is always unique. Like every element when operated with that particular identity will give the element itself. So one group will have only one identity. Now let's prove this. Identity element in a group G means the identity element belonging to G with respect to the binary operation star. Let G star be a group and let E1 and E2 be the two identity elements of G with respect to binary operation star, E1 and E2. Now we have to prove that E is unique. So what we will do, we will take more than one identities and we'll prove the contradiction, right, that it is false. So it proves that there is a unique identity in that, right, and we have to prove that E1 is equal to E2. Now E1 is equal to E1 star E2. Why this? Here we should see that E1 is the element of G. Right, now we are supposing here that E2 is identity. We know that identity element is also the part of the group, right, it is from the members of the group only, right. If E1, if we can consider E1 as the element and E2 as identity, then this condition it satisfies. E2 when operated with E1 will give E1, right, and similarly with this, if we consider that E1 is also an identity, E2 is the element, and then we can get E2 from here. So here we can see that E1 is equal to E2. Let me explain you again. If we can say that E1 is an identity element and element of the group, similarly E2 is also an identity and element of the group, right. In the first case we will take E1 as element. So E1 is equal to E1 in star E2, where E1 is the element and E2 is the identity element. But when we will go to the right hand side, now E2 is the element, E1 is the identity, and we get E2 from here, and so we can say that E1 is equal to E2. So this proves that there is only one identity in the group. Uniqueness of inverse. The inverse of each element of a group is unique. Now about the identity, for the whole group there was one identity, but in case of inverse, element to element it can vary, but each element will have only one inverse. Okay. Now inverse will also be the part of the group only. Let G be a group and let two inverse elements of A and B, A are B and C. That means A cross B will give E and A cross C will also give E, right. This is the property of inverse. See, we can say here, where the identity element in G is B cross E. Now we know that B is equal to we can write B cross E, right, B cross E, and in case of B, here we can in this we can write A cross C. We all know that it is associative, so we can write here B cross A C, right. Here we can write, this is from this we can write it is E star C, right, and this is the identity element, so it will give C only. So B is equal to C. That means for A there will be only one unique identity, either it is B or C. If we are saying that B and C both are the inverses of A, then B and C are equal, right. Uniqueness of the we have done this already. Now if A inverse is the inverse of A, then A inverse of inverse is equal to A. That is, inverse of A is equal to A. We have to prove this now. Now, let G be the non-empty set and A will belong to G. Also, let E be the identity of G with respect to the binary operation star. Then A inverse into A is equal to E. We know this by the groups property, right? Inverse property, if inverse is operated with the element, we get identity element. Now what we will do, we will operate both sides with this element, A inverse into this whole. Similarly, A inverse into this identity element. Now we will open the brackets. It is associative according to the group property. This element will come here and this will go out, right? And this is the identity element. We will get this element again. Now this is the element and this is its inverse. We will get the E here and this A will come here, and this inverse of inverse we will get this, and this is proved. Now let us see, take one example about the group. Let Q plus denote set of all positive rational numbers, and star is an operation defined by A star B is equal to AB by 2, that is AB belongs to the positive rational numbers. Then prove that positive rational numbers with the operation star is an abelian group. Now for an abelian group we have to prove 5 properties: closure, associative, identity, inverse and commutative, right? Now first property is the closure property. We all know that if A and B is a positive rational number, then AB by 2 will also be a rational number, right? Associative, we all know that multiplication or this operation is associative when we are putting a division here. When we are having numerator and denominator, we can associate that part. Identity, let's find out the identity. E star A is equal to A, then E into A by 2 is equal to A. So from here we can derive that E is equal to 2. E is equal to 2, that means E is a rational number, that means it is existing there, so it is satisfying the property of identity matrix. Similarly, inverse, if we can able to find this is equal to identity, we have find out 2, B into A is equal to 2, then inverse we can find out, that is this one, B is equal to 4 by A, and 4 by A is again a rational number, so it has satisfies the inverse property. Commutative property, we all know that A B upon 2 is always equal to B A upon 2. By the product, we know that product is commutative. So we can say that it is satisfying all the properties, so it is a abelian group. Thank you very much.